we can use the log form to solve this. We can also use the exponent form to solve this because this is a related base number. And we can see that a should be equal to 2. Now, your calculator will do this, but really, we can figure this out either from the log form or the exponent form. And right now, we're probably more familiar with solving it this way than seeing it in log form, but that's okay. We're going to get used to seeing it in log form as well, and that's why we want to be able to convert from log to exponent. So here, convert this to a log. Okay, well, the log form doesn't solve this. The exponents form would be where we get the solution. X is equal to 10,000. Okay, here, we convert this to log. Okay, and we wouldn't use the log form to solve this. Okay, the exponent form to solve this, we'd use the log form. Okay, so using the log form, we're going to get, this is not related basis, so I'm going to need to plug this into my calculator again. Log 120, I get 2.07. So x is equal to 2.07, that gives 3 decimals, 2.079. Okay, so again, the main idea, we've done a little bit of calculating using your log button on our calculator, but the bigger part of this is make sure you understand the relationship between an exponential expression and the log expression. Okay, they're the same expression, but defined. One is defined with the inverse operation, one is defined with a regular operation. So lastly here, there are some properties of logs that we should start getting to know. Okay, so the log is only defined when x is bigger than 0, and the base has to be bigger than 0. We run into real big problems when the base is negative or 0. Okay, so we never define logs with bases less than 0. So that's a restriction on the domain of the base and the argument. Okay, and I'll give you an explanation why. So if I have something like this, log base 0 of 5 equals x. Okay, well that's not possible because that means that 0 to the power x equals 5, and that's not possible. You can't get that. Okay, so we can never have base 0. Okay, we can't have negative bases because this issue here, if we have negative 3, for example, and equals pi or something like that, well, negative 3 to an even power is even power would be positive, odd power would be negative, but is pi negative or positive? We don't know. Okay, it's not defined as negative or even or odd. So we don't know if we're going to get negative or positive here for x. So to avoid that, we just say we cannot have negative bases. We have to have positive bases only. Okay, so those are restrictions. So we'll go over those. We'll run into these number of times. But we want to start understanding these restrictions on the base and the argument. These are some properties here. These are what we call identities. Okay, these are identities. The log and the exponent undo each other. So if they undo each other, we should end up with what we started with, which is x. So same thing here. We have an exponent and a log. So there's an exponent, and in the exponent I have a log. They undo each other. I should end up with the argument x here. Okay, and we can show that these are true by just using the definition of log. So if I use this definition of log, I'm going to do this. I'm going to take my base a, and I'm going to put my exponent x on that, x, and that should equal my argument, which is a to the power x. Well, that's true. That must be true. That's always true. Okay, if I do the same thing here, I've got my x, these are my exponent. Okay, so my log always equals my exponent. Okay, when I write a log expression, my base of my log is the base of the original exponent. It's going to be base A, and I'm going to use my argument x. And again, that generates that using my log definition. So that's true as well. Okay, so these are what we call identities. And essentially, this is saying a log undoes an exponent. This is saying an exponent undoes a log.